Hello and welcome back to Engineering Dynamics. I'm your host, Dr. Walck. We ended last video talking about rigid bodies and the three types of motions that we can use to describe them. In this video, I am going to do a couple of examples, and I probably won't work them out numerically, but I want to set them up with you and to understand which equations to use and when, and kind of how to understand how the mechanism itself is operating, how it's moving, how it's rotating. Okay, so our first problem says that a bar AB rotates with a counterclockwise angular velocity of 10 radians per second. It's asking us what the vertical velocity is of the rack and pinion gear. So it wants us to find VR. Okay, so let's just take a look at the mechanism that we have on hand. We have how many rigid bodies, first of all, how many rigid bodies am I looking at? How many do I have in the system? 1, 2, 3, 4. A rack and pinion. If you know what a rack and pinion is, you can go ahead and forward by a little bit. But if not, let me just take a minute to explain what that is. A rack and pinion, a pinion is like a little teeny gear, and a rack is a gear that goes on forever and ever and ever. Well, for as long as your mechanism can hold it, right? So a great example is going to be in your vehicle, in your car, your steering wheel. If you're driving in your car, your steering wheel has a column that goes all the way down. At the very bottom of that column is like a little gear. We call that a little pinion. And that gear, if you turn your wheel, it's going to pull the rack a certain way to change the angle of the front wheels, okay? So as this pinion rotates, so if it rotates, the teeth are going to grab the teeth of the rack, and it is going to pull the rack either up or down, depending on the spin, okay? These are just linkages. These are what we just call it a linkage. And you see two types of pins. We have a pin that looks like this at A, and then we have a pin that looks like this at B. One is an external pin and one is an internal pin. An external pin, so why don't we take rigid body A, B, we take it out and we isolate it over here. This is A, and it goes to B. An external pin means that this thing cannot move up, down, or anywhere. It can't, it's stuck. It's external and it is stuck to the ground. So these lines here in a drawing and an engineering representation, it means that it's fixed. It can't move. So with that in mind, this means that B, the motion of B relative to A, is going to be pure rotation about a fixed axis, and that fixed axis is A. That's a really rough circle, sorry, but yeah, hopefully you understand the gist. So B is going to travel in a perfect world. It's going to travel in a perfect circle around A. So A is an external pin, so it can't move, okay? So all the other particles are going to move about it. But here we have B and C. If we isolate rigid body B, C, it is not grounded. I don't see ground anywhere. That means that this link, it can rotate, it can move, it can do anything. So that means that the motion that we are going to use to describe it is planar. So this is going to be planar motion. I want you to think about the linkage C, I think they called this D, CD. D, that pin looks an awful lot like A. So that means that's an external pin. We see the lines at the bottom, so it means that it's fixed to the ground. It can't move, it's stuck. So it's an external pin. It has a gear, but it has an opening here. So that means that this part is fixed to it. So it's like a gear with a little handle, okay? That means that this gear is going to rotate about this point. So if I asked you what what motion is the rigid body CD undergoing, you would say, okay, and I hope and I know you said pure rotation about a fixed axis, and the fixed axis in this situation is point D. I know you said it. Good job. Okay, so let's figure out how in the world we find VR. My first question to you is, do you remember, and if you don't, I put them up here, the equations that we use? So the bottom equation, it describes pure rotation about a fixed axis. The top one is going to be planar motion. It's planar motion because it has the pure rotation part and it has the translational part. So this has the pure rotation about a fixed axis plus translation, okay? And remember, planar motion, that's the definition of planar motion. It is the combination of translation and pure rotation about a fixed axis. So there is our perfect equation. All right, so how do we apply this? Oh, and remember that this could be represented, this is equivalent to VA equals R omega, okay? So in this case, I only want VR, so VR equals R omega. Now, if you don't, maybe if you don't remember from physics, or maybe your physics teacher didn't teach it, I want to say that all physics teachers teach this. But if not, a rule with gears, there's this condition called no-slip condition. No-slip condition means that at the point of contact, I'm going to write this in pink. At the point of contact, the velocity at that point is the same for both rigid bodies. So I can call this VP. VP is going, or this is like point P, right? So this is VP. VP equals VR. It's the same thing at that point, okay? So and then I also, this is D, so this is also going to be VD. And I know how to represent VD. I represent VD by R omega. Well, what is the distance between the point I'm looking at and the point that it's rotating about? That distance here, well, it's just the radius in this point, so it's going to be 6. Careful, when I analyze later, I know I'm jumping ahead, but I want to point this out while we're here. If I was analyzing the velocity of C, my R would then be the distance between C and D. But since I am interested in the point P, my R will be 6. Okay, and my omega is going to be whatever omega of the gear is, which is omega D. So let's go back to no slip condition. In gears, it is assumed that your system is very lubricated, it has lots and lots of oil in it, and the gears just glide right along each other perfectly. There's no impingement. Impingement means that they can't go inside one another or they can't come apart, okay? They're gliding really nice on each other. So because of that, their linear velocities at that point have to be the same. And their acceleration in the tangential direction also has to be the same. Now, I know this, again, this is like a side lecture, but if you have 2 gears and you have different radiuses, again, the point at where they touch, that velocity will be the same. So say this is A and this is B, so VA will equal VB. The acceleration in the tangential direction of A will also equal the acceleration in the tangential direction of B. My question to you, will AN be the same? No. They will be the same if their radius was the same, but since their radius is different, They will be different, okay? So don't be confused on that. You can only say the radius or the velocity will be the same at the point of contact, and the acceleration in the tangential direction will be the same at the point of contact. Okay. So assuming now that we understand the condition of gears, we can write this equation with confidence. But I don't know omega d. I don't know omega d. I have two unknowns here. I'm looking for the velocity of P, or we can be consistent and call it R, but it's the same thing, okay? I don't know those two. How do I find omega d? Well, lucky for us, point D is also on the rigid body DC, okay? So that means that I can compare points D and C. So why don't we do that? The velocity of C equals, now, the rigid body, CD, is undergoing what type of motion? Pure rotation about a fixed axis, where D is the axis. It's fixed. If you didn't know this, and you just said, oh, it's planar, you could write the whole equation. You could write VC equals BD plus omega CD cross RC with respect to D. And what would happen to the velocity of D? It would go to 0. It goes to 0 because, one, it's an external pin. It can't move, okay? So C is in pure rotation about it, which is why this will simplify to VC equals omega CD cross RC with respect to D. So a few things to note here. When we talk about C relative to D, just make sure you do your homework here, your checks. C goes first, C goes first, okay? That is a must. If C goes first here, and you write a D with respect to C, you are incorrect. Your signs will be off, okay? And it will lead to an incorrect answer. You have to be very careful on these, okay? Also, these are vectors. Can you tell me what unit vector is associated with omega? Well, velocity has to be tangent to a curve. Velocity is in our horizontal plane. And our RC with respect to D is also going to be, so if this is pulling it down, this is probably going to turn this way, right? So if this is turning here, we have our velocity vector here. How would I represent our velocity vector? Let me take a step back. Sorry about that. Okay, so what I'm trying to say, if this gear, our pinion, rotates in the clockwise direction, now I'm assuming that because it is going to push the rack down. And I'm saying the rack is moving down because we were given in the problem that the velocity is going down. So this guy is turning here. If C is rotating about D in pure rotation, that means that my velocity vector is going to look something like this, which is perpendicular to my R vector. And I'm writing my R vector, RC, with respect to D. So my R vector looks like this, where the head is at C, the tail is at D. These two are perpendicular to each other. These are in the radial and the transverse direction, the X and Y direction, whichever coordinate system that you are in, but it's in the horizontal plane, which means that I have to have the third axis present, which is K. So this will have a K unit vector, okay? I'm using XY coordinates right now because I'm given XY coordinates, so we are in Cartesian right now. which is why I said K. If I was in polar, it could be E sub Z, but I'm in Cartesian, so let's use K. Let's write this all the way out. We have omega CD with a unit vector K cross my RC with respect to D. This vector we said was going from D to C. And I see if I project this down to my x-axis, it is 6 inches. If I project this to my y-axis, it is 10, okay? So here, I'm going to have -6, +10. It is -6 because your vector is going in the negative x direction, but it's going in the positive y direction. Please do not mess up those signs, okay? So we have our VC vector, okay? But, oh no, I introduced another unknown. So now I have VR as an unknown. I have omega D as an unknown. I have VC as an unknown. Now, omega D is the same as omega CD. So this is equivalent to omega CD. So really I have 2 equations, I have 3 unknowns. I can't break this up into anything because it still doesn't give me it. So yeah, can't do anything about that. So I need to come up with another equation. And lucky for us, point C is a part of another rigid body. So our next step is to compare C to B. So why don't we go ahead and do that over here. I will write it in blue. Actually, why don't we just do it right here? So let's compare VC equals, ooh, what type of motion is rigid body VC undergoing? Planar motion. If you said that, good job, congratulations. And what type of pins are located at B and C? If you said internal, you are on a roll. All right, so we have VC equals VB plus omega CB cross RC with respect to B. Now, if you notice, I have 2 equations, 1 and 2, that have C in it. You are going to find that this is a trend, and if you set these equal to each other, it is going to get rid of your one of your unknowns. But this gave us another unknown. Another unknown would be VB. So now we have omega CB as an unknown. So we have to write that up here. So we have omega CB and VB. This guy kind of goes away because we can set equation 1 equal to 2. Okay, so in order to do that, I need to find VB. And I can find VB because VB is also on the rigid body AB. So I can say that VB is equal to, what type of motion is the rigid body AB undergoing? Rigid body, pure rotation about a fixed axis, and the axis in question is A. So we have VB equals omega AB cross RA with respect to B. Oh, what mistake did Dr. Walck just make? I put A first where B comes first. This is incorrect. This should be B with respect to A. Okay, and these are all vectors, of course. So here's your trend. This is a known and this is a known. That means that VB is now a known. That means you only have one unknown here and one unknown here. If you set these two equal to each other, you will be able to solve CB and CD. That will then allow you to solve for your answer. Now, some of you are like, Dr. Walck, you solved this backwards. But some of you, when you look at a problem in dynamics, you say, well, it wants the velocity of r. So what do I need to find it? Okay, I have this equation. Oh, I have some unknown, so I'm going to need this, and then I'm going to need this, and then I'm going to need this, and then I'm going to need this. And then by the end of it, you're like, okay, well, I have one known, I'm going to plug it back in, and then I have this, and I'm going to plug it back in, and then I have this, and then I'm going to plug it back in. Oh, my head hurts too. Here are some trends. In these types of problems, you're going to see trends. The first trend is usually what the problem is asking you is at one end of the mechanism. And the problem is usually going to give you all the knowns at the opposite end of the mechanism. So it's not wrong if you start at the end. Okay, if that makes sense in your brain, go for it. For me, it makes bookkeeping a little bit cleaner if I start from where I have all my knowns. So what I'm going to do is I'm going to magically erase this board super fast. Okay, now that the board is magically erased, post-processing is amazing. We are going to start from A and work our way through. So if I read this problem from the very beginning for the very first time, I'm still probably going to write out that the velocity of the rat going down is still equal to r omega. And I'm going to compare the rack to whatever's touching it. Because remember that the way we derive these is that A and B has to be points on the same rigid body. That means that I cannot write the equation VA equals VC plus omega AC cross RA with respect to C. This is absolutely not allowed. It is not legal. Don't even do it. It's because C and A are points on two separate rigid bodies, okay? So we cannot use this method for that. So what we have to do is go from one point to another point on the same rigid body, that point to another point on that rigid body, and then so on and so forth. So I know that I need omega CD. I know that to get omega CD, I need information about C. I need information about D, or B, excuse me. So I'm going to start from A. I'm going to take my first rigid body, and I'm going to, don't be afraid to actually take the rigid body out of the mechanism, if that helps. So you can isolate A, B. So I have rigid body A, B. I have A as an external hinge, B is an internal hinge. I am going to say that B rotates purely about A. So that means that VB equals omega AB cross RB with respect to A. I know omega AB and I know RAB. So let's take a look at this. This is RB with respect to A. So this vector looks like this. Its X component and its Y component. Its X component is 6. Its Y component is 12. Is that correct? Okay. So I'm going to, and omega is given to us as 10 in the clockwise. So my coordinate system here is going to be X and Y, and counterclockwise is positive. So VB, if I were to draw, like represent the vector VB, how would I do that? Well, it's in pure rotation, so I know that it has to be tangential to the circle that it makes about A. I know that. And I also know that it is perpendicular to its position vector. So this is VB, okay? So I'm going to say that VB equals my cross product. If you don't remember a cross product, let's quickly go over it. Because I'm only going to do one of these, and the rest I'm just going to do, I'm just going to keep it in symbols, okay? So you have omega first, so omega has to go in the front row. This is in a K direction only. Remember that. Omega is in the K. If my coordinate system was Y and Z, then my omega would be represented by X. It's always the third variable. But here, my motion occurs in the XY plane, which means it occurs about Z, okay? So that means that this is gonna be 0, 0, omega B is 10, and it is gonna be in the negative direction. RBA, in the X direction, we have 6. In the Y direction, we have 12. And we have 0 in the K because it is planar motion. Okay, so I start with the sign in the letter. The sign is a positive. My direction is I. Then I cover up the column and I do 0 times 0 is 0 minus negative 10 times 12, which would be negative 120. Next step I do is I go to the next column and I take my signs and, oops, this should be a negative, excuse me. I take my signs, I start with a negative, I end with a unit vector J. I hide the column, I do 0 times 0 is 0, minus 6 times negative 10 is negative 60. So I have a final answer of VB equals positive 120I, a negative as a positive, negative 60J. Awesome. Okay, so I now know what VB is. So this mechanism is pushing down. So I know this is hard to see, but this velocity vector is moving this way, C, and we got that from the pure rotation, and this one is moving this way. So this bar is actually being pushed up a little bit. So that means that its angular velocity is going in that direction, whereas the angular velocity of CD is going in the clockwise. So you have two clockwise and a counterclockwise. Okay, so we have our information about the excuse me, B. Now we can compare it to C. So I'm going to say that VC equals rigid body VC is going planar motion. So I'll say VC equals VB plus omega VC cross RC with respect to B. I am allowed to do this because no matter what, if you look at points BC or CB, it doesn't have a relative. It doesn't have a line through it. There's no relative. You can put that in any order. It's still omega, okay? All right. So you just have to make sure that the value is correct. So here we have this. I know this. So I have VC equals, I'm going to plug in my VB. I have 120I minus 60J plus. I have my, let's go for omega BC in the K direction, cross B, RC with respect to B. So that vector looks like this. It does have a slant to it. So it is 16 units across and 2 units down. So this is going to be in the X direction, it's positive 16. In the J direction, it is negative 2. This is equation we're going to label 1. So I have an unknown here. I have an unknown here. But VC, we can come up with another equation that has VC in it because VC is also, the point C is attached to rigid body D. And you can see that C rotates purely about D. So that means that our equation, we'll write it in blue, will be VC equals omega CD cross RC with respect to D. So now I only have two unknowns. I have this unknown and I have this unknown. I am going to set, yes, BC are unknown, right? These two are unknown. But if I set equation 1 equal to 2, it will get rid of my unknown here, and I will only have two unknowns. Do that. We have 120I minus 60J. If we quickly do this cross product here, we should get positive 2 omega BC plus 16, oh, that's in the I direction, excuse me, plus 16 omega BC in the J direction. Now that is going to equal equation 2. So that is going to equal this cross product. So RC with respect to D is going to be a vector that looks like that. So we will have negative 6 in the I, and we will have positive 10 in the J. So this is going to equal negative 10 omega CD in the I minus 6 omega CD in the J. Okay, so now this looks like one gigantic equation, but remember that it is vectors. When you have a vector equation, you can take out the components and equate them, which means take out the i's, set them equal to each other. Take out the j's, set them equal to each other. So here we have 120I plus 2 omega BCI equals negative 10 omega CDI. You can do the same thing with your J components. Your J components will consist of negative 60 plus 16 omega BC equals negative 6 omega CD. Now you know what to do. Now it's just simple steps that you've done 100 times. You're going to solve one equation for one unknown. You're going to plug that back in to the second equation. These two equations, once you solve them, you will get an answer for omega CD and omega BC. You need omega CD. You need omega CD to complete what the question asked for. In dynamics, you have to do all of these steps, and please don't forget what the problem originally asked you for, okay? So make sure you go back and you say, okay, the velocity of our rack is equal to the radius of the pinion multiplied by its angular velocity. So your final equation of VR is going to equal 6 times omega CD, and you are finished. I am so winded. But I did say in the beginning of this video that I would do a few examples. I kind of lied. I'm going to go with a couple. Let's look at one more example. We'll run through it just using equations so you can see like expressions. I don't want to solve it out or anything. If you're interested, put it in the comments and I can always post the solutions. But what I want to do now is just kind of drive home the patterns that you're going to see. You are going to see that you are asked for something at the end, you are given for something at the beginning, and you can usually always set two equations equal to each other and then solve them like in a systems equations, okay? Okay, so let's take a look at our second example. Okay, so our second example is shown here. It's just saying like at this position, don't worry about it moving or anything. It's just at this position in this moment of time, a bar AB has a constant angular velocity of 6 radians per second in the counterclockwise direction. It's asking us to find the angular velocities of both bars, BC and CD, at the instant shown. Okay, so to review, we have how many rigid bodies in this one system? If you said 3, you are correct. So we have one rigid body, which goes from A to B. We have 2 from B to C, and our last one is C to D. So again, we can isolate each rigid body. So this is A, to B. This has a length of 0.25, and it is traveling. It's rotating like that. Okay, so what type of pin is located at A? You said external, you are correct. And that means that at B, it's an internal pin. If it is rotating this way, that means that it's pushing the bar, right? So it has to be, B is in pure rotation about A. So the velocity has to be tangential to the curve and perpendicular to the position vector. So our position vector is RB with respect to A, and our velocity vector is straight up. Okay, and we want to represent or calculate VB with respect to A. So VB equals, this is pure rotation. Now, what is the linear velocity of A? It is 0. That's how I know B is in pure rotation. Anything with an external hinge has a velocity of 0 and an acceleration in the tangential direction at 0. So what can you tell me right here about velocity of point D? It equals 0, okay? All right, so velocity of B equals omega AB cross RB with respect to A. We are given omega AB, and we know all of the units. So that means that VB is now a known. Okay, now this one, if it was up to me, I would probably I'd probably do the same thing for CD before I did CB, but why don't we do CB first, and you will see why. So if I isolate my rigid body, VC, I already defined my velocity vector B, so it still has to be this, okay? Now, if I were to draw my velocity vector C, I honestly am not sure how I would do that. I'm not sure I would know. So I am going to put a pause on that, and I'm going to say, well, let me take a look real fast at what rigid body CD tells me. Well, C has to rotate about D. Its velocity has to be perpendicular to the position vector, but tangential to the curve. Now, if my mechanism is being lifted up here, I'm assuming this is going that way. So I'm going to say that my velocity vector of C is perpendicular to the position vector and tangential to the curve. So now I can go back here and say that it is kind of like that. Okay, so now I kind of get a visual of what everything is going. And I like to draw this because my answer for velocity of B, it better only be a value in the J direction. Here, my velocity at C, the final velocity, should be some negative value in the X and some positive value in the J. So drawing this kind of helps me understand if I'm on the right track and my answer is making sense. Okay, so let's now go ahead and write the equation VC equals VB. I'm doing VC equals VB, but that doesn't mean that you can't do it the other way around. You are totally welcome to do VC equals or VB equals VC. I'm not going to because it's a known, so I'm going to put it in the equation. So VC equals VB plus omega BC cross RC with respect to B. This is a known. This is an unknown. This is a known. This is an unknown. But here is our trend. C also belongs to a rigid body, CD. So I can say that VC also equals, this undergoes pure rotation, so it is going to equal omega CD cross R C with respect to D. So now, I don't know this, I do know this. I want to set these two equal to each other. If I do that, my three unknowns become two, and then I'm in good shape, okay? See, I told you there was a pattern. So let's do that. So let's do, I really hope you guys can see green. Okay, so let's do VB plus omega BC cross RC with respect to B equals omega CD cross RC with respect to D. Now, this looks like one big equation, but it's a vector and it is planar, so you have two components. So now you can break these components out into I and J, and you can solve for omega CD and omega BC. And remember that that was your goal all along. So that describes translational motion. We have our translational motion. That also went over pure rotation about a fixed axis. That is this portion of the equation. And we also went over planar motion, which is the whole kit and caboodle, right? All right, so I hope that video helped. If you like it, give it a thumbs up, and I hope you subscribe. If you have questions, put them below. I will answer you. Thank you so much, and I'll see you next time.